What are common PID controller tuning problems? Imagine trying to tune a musical instrument but ending up with a sound that's off-key or out of sync. Tuning a PID controller can be just as tricky, and many engineers face similar challenges. When working with systems in electrical engineering, control systems, or signal processing, getting the right balance of the proportional, integral, and derivative gains is essential. But often, problems pop up that make the system less stable or less responsive. One common issue is instability and oscillations. If the proportional gain is set too high, the system can start to oscillate or even become unstable. It's like pushing the throttle too hard and causing the system to overshoot and shake. This happens because the controller overreacts to errors, leading to continuous overshoot of the set point. Engineers often find this during the initial tuning phase when they increase the proportional gain until they see these oscillations, similar to the Ziegler-Nichols method. Another problem is excessive overshoot. When the system output goes beyond the desired value before settling, it's called overshoot. High proportional or integral gains can cause this. The integral part, which sums errors over time to eliminate steady-state error, can make the overshoot worse if it's too aggressive. The derivative part helps to dampen this effect by slowing down the response, but if it's not tuned properly, it can cause other issues like noise amplification. Slow response and lag are also common. If the gains are set too low, the system responds sluggishly to changes or disturbances. This means it takes longer to reach the set point or recover from a disturbance, which can be frustrating in real-world applications. Proper tuning involves finding a balance where the system responds quickly without overshooting or oscillating. Steady-state error is another challenge. Without enough integral gain, the system might never fully reach the set point and stay slightly off. The integral component is responsible for eliminating this persistent offset by accumulating the error over time and adjusting the control output accordingly. Sensitivity to noise is a tricky problem too. The derivative term reacts to how fast the error is changing. If the sensor signals are noisy, the derivative can cause rapid fluctuations in the control output. This can lead to instability or excessive actuator wear. To fix this, engineers often reduce the derivative gain or add filters to smooth out the noise. Integral windup is a less obvious problem. When the actuator is saturated or cannot respond, the integral term keeps accumulating error. Once the actuator becomes responsive again, this large accumulated error can cause overshoot or long recovery times. Anti-windup strategies, like limiting the integral value, help prevent this issue. Tuning a PID controller involves balancing many trade-offs. Increasing the integral gain reduces steady-state error but can cause overshoot and oscillations. Increasing the derivative gain can reduce overshoot but makes the system more sensitive to noise. Fine-tuning these gains takes time and experience, often using systematic methods like the Ziegler-Nichols or Cohen-Kuhn techniques. These methods observe how the system responds to certain inputs and help set initial gains, but they usually need further adjustment for the specific system. In the end, the main problems with PID tuning come from trying to find the right mix of responsiveness, stability, and robustness. Proper adjustment of the proportional, integral, and derivative gains is key to avoiding instability, overshoot, slow response, steady-state error, noise sensitivity, and windup. When tuned correctly, a PID controller can keep systems running smoothly and efficiently in electrical engineering and control systems.